Alright, hello everybody. So as you know, my name is Mr. Klein, and this is my first video where I'm trying to do some flipped learning with you for our first unit in IB chemistry. So this unit, as you can see, it's called Measurement and Data Processing. And so I'm just doing the first part of your IB textbook for chapter 11. That's units or topic 11.1 and 11.2. 11.3, which talks about all of the different types of techniques that you can use. We're going to do that later on. So now, let's go and take a look at what we're going to talk about for this part of the topic. And mainly what we're going to talk about is data. How can we take data and manipulate it? How can we deal with errors? That's what we're going to look at. And so our first real slide here talks about different kinds of data. So you have the first kind of data, which is called qualitative data. Now you're going to be doing your IAs, you've already started this process, and so what you'll notice is that I want qualitative data. Now you haven't collected any data yet, but when you are doing an experiment, you need to make observations. So these observations, this is what you need to put into your IA as part of your data set. Just like you do with quantitative data, where you talk about numbers, measurements that you took, you also need to include qualitative, non-numerical information. These are your, five senses that you're using. Things like, well, was there a color change? So if there's a color change, you really need to say that. Was there a precipitate formed? What color was the precipitate? Now, if you want to then, do something quantitative with this, you would do things like, well, what's the mass of that? What's the volume? You've heard this stuff before. You've been doing this for a really, really long time. And so this is just another extension of this. Now you're really going to have to think about what's the data that I'm collecting. Please do not stick to only qualitative data. You need to include something quantitative in your lab reports. The only time where we will do strictly qualitative analysis is when we're doing something called a qualitative analysis. And that is where you are looking to see if there is something present or not in a sample. And we'll actually do a little mini lab like that, identifying unknown ions. Otherwise, you're going to be taking measurements. Now, the problem with quantitative data is that you're always going to have some kind of error associated with it. And this is what drives students crazy. The error analysis, looking at what you did wrong. Even if you took the perfect measurement, guess what? Your machinery, your equipment, has some kind of random error associated with it that you have no control over. And you have to take that into account. So this brings us to our next big idea here, which is precision and accuracy. What's the difference between them? Unfortunately, people seem to use these interchangeably. When you hear about people talking about a precise measurement, a lot of times they're talking about how accurate it is, and they're misusing it. When I talk about precision, I'm mainly really interested in reproducibility. So how close a repeated measurement is to another. You could be precise, and yet you could actually be inaccurate because your result may not be close to the true value. Is your answer correct? Well, you could be precise, yet you could be inaccurate. And so when I look at my scenario here, I have my 2 or 4 dart boards set up, and what I can see on the left here is I have somebody who's very reproducible. They've reproduced the same terrible archery pattern over and over again. But they're not accurate because they're not in the bullseye. Over here, the second one, this is me actually shooting an arrow. So here I have a situation where I don't get reproducible results at all, but I also don't get anything that's accurate. So I actually have this situation where I'm neither accurate nor precise. And these last two here, these are important to look at. So I could be accurate, and I could do one trial and be accurate, but that's a problem with chemistry and with science in general. You really need to do more than one trial. Because that first trial could be accurate, but then your repeated trials, well, maybe you'll get a mark up here, and maybe you'll get a mark down here. And at that point, you're no longer accurate, really, because now you have two other trials that are completely inaccurate, and you're not precise. This is your best case scenario right here, where you're accurate and you are precise. So this is my best case. This is what we strive for. You want to be accurate, you want to be precise. You want to get hundreds on your tests, accurate. You want to do that over and over again. So take a second here, look at this archery pattern, and pause the video and fill this out. And write, accurate, precise, yes, no. And then tomorrow in class, when we look at this together, we'll talk about it. This will be one of your homework things that you need to do. Okay, the IB unfortunately wants to torture you with experimental errors. So they look at this and they want you to mention the types of errors that could occur. And so the first type of error that could occur is a systematic error. In general, error is talking about, how much fluctuation is there in a measurement? How much variation do we have? We have this systematic error. So this is something that could be instrumental. The instrument is not calibrated correctly, or you never set the scale to 0, or you have some problem where you're measuring the same way over and over again, and every time it is wrong. The problem with these systematic errors is that you could collect as much data as you want. You could collect data all day long, but you will keep making the same mistake. You will not zero the scale. You will have an issue where you will not do the correct thing, and you will keep getting the same precise result over and over again, but it will be inaccurate. And when I look down here, here's a funny example of, this very serious scientist, and they've totally ignored the fact that there is a rock in the bottom of their graduated cylinder. And so they have this inaccurate measurement, but they're blind to it. They don't see it. And so they keep making these measurements in this graduated cylinder, and yet they cannot figure out the fact that it is wrong. And so they'll have a mistake in all their measurements. They could do this all day, it won't make a difference. The other kind of error is a random error. And this one, your result could either be too high or too low. This is where you make mistakes that are random. You could read the meniscus from above it or below it. And in both cases, you're going to get different mistakes. But what generally happens is that your random errors get less and less because you get better at it. And so you can actually reduce the amount of random errors by taking a lot of measurements. You'll get an average that'll be close to a correct value. This is where we would do something like standard deviation. We'd want to see how random you were. Is your result due to chance or not? We'll talk about doing standard deviation, but this is a case where you can reduce that error by taking more than one measurement. Okay, well, what do random errors in measurements look like? Well, all equipment that you use has some kind of tolerance associated with it. This tolerance is based on the equipment. Some equipment has a very high tolerance, meaning that you have a situation where you can get a very accurate reading because you can go to the tenths place, hundredths place, or even thousandths place if you're using something like an analytical balance. Now we're going to use two types of equipment. We have analog equipment and digital equipment. The analog equipment, what you can do is you can estimate to one place after the smallest increment. So let's take, for example, that I had something like a thermometer and I was measuring a warm water bath at 45 degrees Celsius. Well, on the scale it says 45 degrees Celsius and the next increment is 46 degrees Celsius. Well, that means that I'm between those two. I'm going to be guessing where I am between them, somewhere in here. So I could put down 45.3 degrees Celsius, and that would be a guess to some degree. Because although I know that it is between 45 and 46 for sure, I don't know exactly where. My lab partner could say, no, it's 45.4, and they would be correct as well. We just don't know. And so what we say is that analog equipment has an uncertainty of half a degree or half an increment. So if I were to write this, it would be 45.3 degrees Celsius plus or minus 0.5 degrees Celsius. And that's because the smallest increment in this case is 1 degree Celsius. So I'm going to be plus or minus a half. So what that means is that I am somewhere between this 45.3, where I have something 0.5 less. So that would be 44 minus 0.5 would be 44.8, or I could be 45.8. And so this is within my tolerance of the equipment. Now if I have a digital piece of equipment, if I was measuring the temperature and the thermometer said that it was 45 degrees Celsius on a digital thermometer, well then at that point I would say, well, I could be either 44 or 46. So here it's plus or minus 1 degree Celsius. So now, when I look at this, I'm like, okay, well, I could be 46 or 44, plus or minus 1 degree Celsius. So with digital equipment, when I look at this, I'm plus or minus 1 increment. With analog, I'm plus or minus 1/2 increment. Now, when I have a certain range of uncertainty, I have to take this into account. So these next slides here, they show you different examples. So here with this, I have my thermometer again, and now it records to the tenths place. And so my equipment could be plus or minus that smallest increment, so that's plus or minus 0.1. Here's another analog example. And here are some examples that I want you to try now on your own. Come into class tomorrow with these. Let's go over them together. Let's spend the time reading each of these. Now that you've seen sort of how to do this, it's time for you to practice. Here's another example with a graduated cylinder. And then after that, we'll talk about significant figures and what they mean. But for now, we're going to talk about reading equipment, and you're going to practice reading equipment on these slides and try them for homework. Thanks so much.